Okay, great. Then let's move on to our final talk of this session, which will be given by Emma Dahl. The title is Color and Structure of Jupiter's Clouds During the Juno Era. Looks great.
Okay, you can see it? Looks okay? Okay, can you hear me?
Take it away.
Can you hear me okay, Nancy? Test, test, hello?
Yeah, we can hear you.
You can hear, okay, thank you. Oh, I think Nancy might have frozen, or at least for me. But at any rate, I'll go ahead and get started. So my name's Emma. I'm a graduate student at New Mexico State University. I have been working with Nancy Chanavert on measuring the color and structure of Jupiter's clouds during the Juno era. I am defending in less than a month, so I have a foot out the door. But this is basically going to be kind of a baby dissertation talk. I'm going to try really hard to not go over time. But basically, the 3.5 meter has enabled this whole project, so I'm going to focus on that. Okay, quick outline. I'll go over the background and motivation for this work. I'm going to discuss the instrument that we built and the data that we used or that we've captured. And then I'm going to go over the science that we've done, so the radiative transfer modeling, and then the two projects that I've done, one of which is completed and one of which is very much still in progress. And then I'll go over some future work and conclusions. Oh, there's Nancy, she's back, okay.
So sorry, my Zoom totally crashed. I'm glad you carried on without me.
Yeah, I have extra time now, so that's good. Okay,
great, so, yeah, you're off.
So the background and the important motivation for this work, there's basically three important points to cover. So mainly, so first off, there's the fact that we have a pretty good theoretical estimate of Jupiter's cloud composition and where those clouds are in the atmosphere. And we think that, oh, the Slack is blowing up. We think that the uppermost cloud deck, there's 3 cloud layers. We think that the uppermost one is ammonia ice with a base at 0.7 bars. But about the last 3 decades of, and even before then, of modeling and observations show that these might not be safe assumptions about the cloud layers. It's hard to confirm that the uppermost cloud deck is made of ammonia, and we can fit these data with deeper clouds or different cloud formations. It's also a big unknown what the coloring agent or the chromophore is that gives Jupiter's clouds their colors. It's still a mystery as to what exactly that is. There's been a lot of work done on this. We're pretty sure that there's 1 to 2 chromophores total. And we think that we still don't know exactly what it's made of. The favorite candidates at the moment are either irradiated ammonium hydrosulfide or photolysed ammonia reacting with acetylene in the products of those reactions. And the other important piece of context is that the Juno spacecraft is at Jupiter. It arrived in July 2016, and Juno has been doing a great job of probing the deep atmosphere at high resolution, but it has really limited spectral resolution in the optical regime. So it sort of leaves, there's this gap in parameter space that covers the uppermost cloud deck. And so what kind of falls out of all these things are these major science questions that I've been trying to answer for the last 6 years, which is what is the structure of Jupiter's uppermost cloud deck and what causes the color of Jupiter's clouds? So we, with the help of engineers at NMSU, we built and characterized this instrument called the NMSU Acousto-Optic Imaging Camera, or NAIC. There's a top-down view of it. Sorry that I have things labeled, but not the actually what those elements are. If you want to know more about the instrument later, you can ask me. I'm happy to talk about it. But NAIC is interesting in that it has a unique filtering element called an acousto-optic tunable filter, or AOTF. And AOTFs are basically birefringent crystals, or they use birefringent crystals that have high elasto-optic coefficients. And what that means is this index of refraction changes readily when you apply a standing acoustic wave to it. And it basically will act like a diffraction grating as a result of that. And depending on the frequency of the sound wave that you apply to the crystal, it'll spit out a diffracted beam at a different wavelength. So you can technically tune the crystal to spit out a different wavelength. And I have this video I love to show. This is in the lab. This is looking back through the output window of the AOTF as we're cycling through wavelengths really quickly. This is basically from the perspective of the CCD within NAIC. So this is what we do when we image Jupiter too, but we do it much more slowly. It takes more time. So when we use NAIC, we take 241 images every 2 nanometers from 470 to 950 nanometers. And then we take those images and we stack them on top of each other. So that, and into a cube, or into what's called a hyperspectral image cube, where the X and Y axes are, position. And then in the Z direction, it's wavelength. So you can, in theory or in practice, you can pick a pixel that's over some location on Jupiter, and you can drill down through wavelength space and extract a spectrum from that location. So what did we do with NAIC? We conducted a 5-year-long observing campaign at Apache Point Observatory in support of the Juno mission. Basically, as a part of an international ground-based observing campaign, people all over the world observing Jupiter in different wavelength regimes in support of the Juno mission. And what did we do? We conducted an observing run with a 3.5 meter whenever Juno completed a close peridrome pass every 2 months or so, and whenever Earth-based viewing geometry allowed. So we totaled 36 half nights over 5 years. And then I did the math the other day. In total NAIC, we got 150,000 plus images with NAIC, and that includes lab data and stuff. So that's just kind of a fun number. So we have a lot of data and we have lots to do with it. Okay, so here's an example of some of the data that we can get. So like I said, we stack our images into these hyperspectral image cubes, but these images here are basically slices of that cube at certain wavelengths. So I just want to point out, so here's 480 nanometers, so here's really blue, here's the great red spot. You can see the signature of the chromophore here because it's absorbing a lot of the blue light, and that's the signature of the chromophore basically. It's not so much a red chromophore as it is very anti-blue. So here you can really see the great red spot popping out. And then at 890 nanometers, so it's with 890 nanometers is within a methane absorption band. And methane absorption bands in Jupiter's atmosphere are basically a really good probe of altitude. So you can see the great red spot towering above clouds that surround it. And so it's brighter relatively than the surrounding clouds. And then also Io's photobombing up here. And Io is obviously far above the methane gas, so it's really bright. So we have a lot of data that looks like this. So what did we do with the data? We did radiative transfer modeling, and we used the nonlinear optimal estimator for multivariate spectral analysis, or NEMESIS, to model our spectra. NEMESIS is a powerful and flexible radiative transfer code originally developed for use with Cassini series data. And then within NEMESIS, we parameterize our clouds using something called the creme brulee model. And the creme brulee model assumes that the uppermost cloud deck is a thick tropospheric cloud layer with a relatively thin chromophore layer directly on top of it, just like the crust on a creme brulee, and then a stratospheric haze layer above that as well. And the other important part of the creme brulee model is what it assumes about color. So it uses, so I mentioned the chromophore candidate, that is the photolysed ammonia that reacts with acetylene. It assumes that that chromophore candidate is a universal coloring agent in the atmosphere, and it's present everywhere, but present in different amounts. So it lends Jupiter its very red color just by being present in different amounts everywhere. So this is a plot down here. This is imaginary index of refraction as a function of wavelength of that chromophore candidate. And you can really think of this as a plot of extinction versus wavelength, or absorptivity. So like I said before, the chromophore does a really good job of absorbing all of that blue light. So that's the signature of the chromophore that we're looking for. Okay, so project 1. So this is the first project. We just published a paper on this earlier this year. And we tested the validity of the creme brulee model using data from Peridrome 5, which happened in March 2017. So Juno's 5th peridrome pass of the planet. And we took spectra of 3 major cloud features. Hopefully, can you see my cursor maybe? Hopefully you can. Yeah, okay, Hannah's nodding. We took spectra of the north equatorial belt up here, of the equatorial zone here, and the south equatorial belt down here. And what's interesting is you can see this whitish cloud here in the SEB in the south equatorial belt, and that's an outbreak cloud, which is thought to be like kind of a strong convective storm system that sort of bursts up through the cloud tops from deeper in the atmosphere. So it's this fresh overturned material, basically. We thought that would be interesting to look at. And we ran 4 sets of models where we had either different assumptions about particle size, because those are hard to retrieve from these data. And then we also ran models with and without allowing the chromophore complex or imaginary index of refraction to vary. And the idea there was that if, the model with the fixed chromophore didn't fit the spectra as well as the one where we let it vary, then that was evidence towards either this isn't a good parameterization or we need to use a different chromophore, or there's a different candidate that we need to figure out. But what happened was all models produced pretty good spectral fits across the board. The cloud structure results were comparable to previous works, except the SEB cloud looked pretty optically thick, maybe unphysically optically thick. So that was some evidence, and which has happened in previous works too. So it's, evidence that maybe we need to use a different parameterization for these sort of major outbreak clouds or unique weather events. And then we also found interesting evidence when we did let the chromophore vary, that there might be a younger or more reflective chromophore, the same chromophore, but just less irradiated by ultraviolet light present in areas of upwelling and overturn, like in the SEB outbreak cloud. Right, so if you want to read more about this, you can go find my paper in the PSJ. Next slide, there we go. Okay, so here's project 2, how am I on time? A couple minutes, okay. So this is project 2 that I'm currently working on at the moment, while also writing my dissertation. So it's very much in progress still. And we're trying to test a modified creme brulee model with a Parajove 19 data set from April 2019. Whereas in this data set, something interesting, so we had the SEB outbreak in the last data set. Here we have the disturbed equatorial zone. So when the equatorial zone undergoes a disturbance, it turns a dark reddish color, and the clouds below it usually clear out. So here's for reference, there's the equatorial zone in March 2017 at a similar wavelength. It's much brighter in the blue. So what's going on there? I'm trying to figure it out. Okay, so here's a comparison of Parajove 5, the equatorial zone from Parajove 5, when it was quiescent compared to the Parajove 19 disturbed equatorial zone in blue. And so the difference between these spectra here in the blue, that's the signature of the chromophore that we want to test and look for. And then also the 890 nanometer methane band that I mentioned earlier, you can see that it's more shallow in the Parajove 19 data. That's some evidence for either an extended haze or a higher cloud top. So we're trying to figure out what's going on here. We're trying to test both the classical creme brulee model and modified versions to see what it can tell us about what caused that change in cloud structure. I'll kind of skim over that, but we have some preliminary results, but it will, a paper on this will come out eventually. Okay, so I'll wrap up really quickly. So the main takeaway so far, or I guess as a result of this and the ongoing project, is that the creme brulee model is a valid parameterization of Jupiter's atmosphere, but maybe not for unique weather events, or there's something else going on there that we need to account for in our cloud models. And it looks like the Carlson chromophore does seem universal, but maybe in these fresher weather features, or even in the older weather features, there's difference in the chromophore spectrum just because it's aged up or down, basically. So we have a few papers resulting from these data sets from APO. Yeah, the first one's a very, very liberal in prep at the moment. You can go check out these other works, a lot of conference proceedings. And then future work, we might potentially use these data. I've had a colleague suggest that we can use it to calibrate GenoCam data. And we can compare it to other data that we're taking at the same time. And then I guess I'll wrap up, and you can, my contact info is there if you want to ask me more about all of this good stuff that I've been working on. I think that's it. Oh, only over time by 30 seconds. That's not bad.
All right, thanks, Emma. Let me figure out how to get rid of this background. And in the meantime, let me pause and see if there are any questions from the audience. Anyone have any questions for Emma? I'm too busy watching the screen, so just ignore the red behind me while I figure out how to do that. But in the meantime, I'll ask a question, because this is a meeting, designed to showcase results from APO and perhaps engender some crosstalk. And so I guess I was curious, sort of what I mean, I know that having the ability to host a guest instrument on the NA2 port is obviously critical for this experiment, but I guess what else about, is there anything else about the way APO is designed? And it doesn't have to be sort of the optical design, but just sort of the way anything about the facility or observatory is designed that made this project either possible or easier or anything like that.
I think the main thing is just the people that work there, like all the ob specs. Russet especially has been very helpful. All of the day staff. I mean, because we've kind of been up in everyone's hair, like whenever we have to go up there to bring the visiting instrument. So I think that everyone's hard work to accommodate us and make sure that we can get the data that we need has been, a boon to this project. I think that's the main. I mean, that's the main thing. Other than, yeah, like you said, like it's, sometimes we would leave NAIC, we would store it up on the dome floor, and then it would be really easy to just roll it over and stick it on the NA2 port. So like that was pretty painless. You should build an elevator up to the dome floor. That would have made our job easier, so we didn't have to carry NAIC up the stairs all the time. But
Noted.
Yeah. But other than that, although we did use that one. There's that. I don't know exactly what you would call it. There's that net that you can use to like loft stuff up there. I think we used that once for NAIC, but that was a little scary. But yeah, lots of adventures and observing and being up there on site all the time, which was great. So
yeah. Okay, any final questions before we close out this session? All right, well, thanks everyone so much for your attendance and your participation. Thanks to all of the speakers for this second session of the morning.